Hey guys, this is a lesson on infinite limits. There's a shortcut to do so bear with me and we'll get through this set of notes. Um, so limits that approach infinity, positive or negative, it doesn't matter which one, are used to determine where the function has a horizontal asymptote. That would be an asymptote that goes from the left to the right. So when x approaches positive or negative infinity of a function, the value of the limit will be the horizontal asymptote. And when there's a horizontal asymptote, it will always be y equals the asymptote value. So infinite limits will equal the value of the horizontal asymptote of the function. And that could give you one horizontal asymptote, two horizontal asymptotes. It just depends on what your function is. If the function approaches infinity in the denominator, then the limit is 0. Then you'll have the following, where c is a constant and p is an integer greater than 1. So if I had the limit of some constant, we could pretend it's 5. Divided by x raised to, we'll just say an integer greater than 1, we'll say 3. As x approaches infinity, the best way to think about this is if I have some number divided by infinity, oh my goodness, try again, infinity raised to the third power, that's still going to be 5 divided by infinity. So if I have some small number 5 divided by a huge number infinity, whatever infinity is, because it's a number that's never reached, it's going to be a really small fraction. So that's eventually going to approach 0. So if I end up with infinity in my denominator, I'm going to end up with a limit that equals 0. Same with negative infinity. If I had a really small number as x approaches a negative infinity, and we'll keep the constant 5 divided by x to the third, that would still be 5 divided by negative infinity to the third, which gives me 5 divided by negative infinity, which is still going to give me 0. So if I have the limit as x approaching infinity of the function 10 divided by x squared, I plugged in my infinity, I get 10 divided by infinity squared, which still gives me 10 divided by infinity, because infinity times infinity is still going to give you infinity, which is going to be a small number, 10 divided by a huge number, which is going to approach 0. And even if I had a larger number in the numerator, like 2,500, or sorry, not 2,500, 2,500,000, divided by negative infinity to the fifth, I'd get 2,500,000 divided by negative infinity, because if I multiply a negative 5 times, raised to the fifth power, I get a negative. That's still going to give me 0, because I have 2,500,000, which still is a small number compared to infinity. Dividing by infinity is still going to approach 0, because my larger number is in my denominator. Sometimes if you're stuck on limits of functions, something like e raised to the x, especially if I'm plugging in infinity or negative infinity, you're better off typing it in the calculator and looking at the graph. So if I broke my graph up into two parts, positive side of x would reach positive infinity. Negative side of the y-axis would reach negative infinity. So if I'm going to the positive side, that would be this side. The right side. Where is my graph going to? And remember, limits always equal the y value of the function. So where is my graph going to? Well, it's going to positive infinity. If I had limit of e raised to the negative x as x approaches infinity, so I looked at that graph, well, I break up my two parts. I have approaches positive infinity on the right side, negative infinity on the left side. Looking at the left side of my graph, nope, sorry, we're going to positive infinity, so looking at the right side of my graph, where's this curve going to approach? Well, it's going to get infinitely close to the x-axis, which is going to be a y value of 0. So here's the shortcut, and it has to be for limits that are determined to be indeterminate. That means you can't find the answer, because you end up with something like 0 divided by 0, or zeros in the denominator, or if you have infinity divided by infinity, that's also considered indeterminate. So indeterminate just means you can't solve it, can't find the answer. So you have to do something to the function in order to find the limit. And this is specifically for limits that approach positive and negative infinity. So L'Hopital's rule is what it's called. Is if I have the limit of f of x divided by g of x, which is two separate functions. They could be polynomials. That's usually what this is used for. As it approaches positive or negative infinity, it doesn't really matter which one. You just have to be careful when you're plugging in, if it's positive or negative. That's the same thing as when you take the derivative of the function and evaluate the limit. And you can do that as many times as needed. So the numerator and denominator are simplified so you can figure out the limit. So what that says is if the limit of the original function is indeterminate, meaning you can't figure out the answer, then you can take the derivative as many times as you need to of the numerator and denominator to determine the limit of the simplified fraction. So looking at number 1, if I were to plug in infinity in my numerator and denominator, I'm going to end up with infinity divided by infinity, because no matter what I multiply infinity by, 4 times infinity plus 3, I'm still going to get infinity. And 2 times infinity minus 1, still going to be infinity. You're not comparing infinity to infinity, which infinity is larger, because infinity is infinity itself. So there's no comparing infinity. So you have to simplify the function before you do that. So if I were to take the derivative of my numerator and denominator, I'm still having the limit, because I didn't evaluate the limit yet. Well, the derivative of 4x plus 3 would just be 4, right? And the derivative of 2x minus 1 would just become 2. So if I take the limit as x approaches infinity of 4 over 2, that's really the limit as x approaches infinity of just 2. So looking at that, is there anything I could plug into my function 2 now that it's simplified when I use L'Hopital's rule? No. So my limit is just going to be 2. Now looking at the next one. If I had the limit as x approaches negative infinity of x plus 4 divided by 3x squared plus 5x minus 2. Well, if I plug in infinity, I'm still going to get infinity over infinity. So I need to simplify my rational function over here. So if I take the derivative of my numerator, I end up with 1. Derivative of my denominator, well, I'm going to end up with 6x plus 5. That's simple enough where if I plug in infinity, I can figure out what it is. So I get the limit as x approaches negative infinity. So you could plug in here, but if you wanted to take it further, what's the derivative of 1? Well, that's 0. And then what's the derivative of 6x plus 5? That just gives me 6. So if I continue to take my derivative, I end up with 0 divided by 6, which still gives me 0. If I didn't do that, we just talked about it, and I plugged in infinity, well, here I'd plug in negative infinity. 1 divided by 6 times negative infinity plus 5 still gives me 1 divided by, well, negative infinity times 6 would be negative infinity, plus 5 is still going to be negative infinity, and that would still give me 0. So you can keep on taking the derivative until you feel comfortable of plugging in infinity and evaluating it, or you can simplify it far enough and then plug in infinity and figure it out. Whatever you want to do. You can keep on going until you can't take the derivative anymore, or take it once and plug in infinity and figure out what it is. So the last one on this page, I take the derivative of my rational function. As x approaches negative infinity, I would have 15x squared plus 10x divided by 1 minus 8x, right? So if I plug in infinity, I'm still going to get infinity over infinity. So we'll try something else. Take the derivative again. So the limit as x approaches negative infinity of, this would become 30x plus 10 divided by, well, derivative of 1 is going to become 0, so I don't have to write that, but if you wanted to, you could. And derivative of negative 8x would just become negative 8. And again, if you want to keep on going, you can. So I'd have the limit as x approaches infinity, negative infinity, sorry, of 30 divided by 0 I get 0 on the bottom. So there is a point where I need to stop, because I would get 0 on the bottom, so that's too far, because that makes it indeterminate, so that doesn't help. So this is as simple as I can go before I plug in negative infinity. So I would have 30 times negative infinity plus 10 divided by negative 8, which 30 times negative infinity is going to be negative infinity plus 10 divided by negative 8. Well, is negative infinity plus 10 really going to make much of a difference of negative infinity? No. So it would be negative infinity divided by negative 8. Well, that you can simplify. If I divide by a negative, that would become positive. So I end up with positive infinity as my answer. So, does anybody see a pattern in the examples above? So if we zoom out here, what ends up happening with each of the functions? The first one ended up being 4 divided by 2. Okay. The second one ended up being 1 divided by 6x plus 5. The last one ended up being 30x plus 10 divided by negative 8. What happens? It has something to do with the highest powered terms. Meaning the ones with the highest exponents. And that's what L'Hopital's rule is all about. It's a shortcut. So, the summary of L'Hopital's rule is saying if a limit of a rational polynomial function is approaching positive or negative infinity, you can use the terms that have the highest powers in the numerator. So if we're looking at the three cases that L'Hopital's rule is with polynomials, the first one is when the limit equals 0, and that's when the higher power is in the denominator. So if I'm looking at my rational polynomial right here, I got 10x to the 6th minus 8x to the 3rd divided by 4x to the 5th minus 8x to the 7th. So if I'm looking at the ones with the highest power in my numerator and my denominator, that would be 10x to the 6th in my numerator and negative 8x to the 7th in my denominator. So those are the two I want to focus on. So when I take the limit, I can just focus on those two. So the limit as x approaches negative infinity of 10x to the 6th divided by negative 8x to the 7th. Well, I can reduce that. All my x's in my numerator would cancel with all but one of my x's in my denominator. And then I would end up with the limit as x approaches negative infinity of 10 divided by negative 8x, which still reduces because 10 and 8 will reduce, but you don't have to reduce it because when I plug in negative infinity into my x term, I get the limit, oops, no longer limit because I'm actually evaluating it, of 10 divided by negative 8 times negative infinity, which would give me 10 divided by negative 8 times negative infinity would change to a positive infinity, which ends up being 0, because I have infinity on my denominator. Whoops, that's supposed to say positive. So if I have the limit equals positive or negative infinity, that's when the highest power is in the numerator. So looking at number 2, my highest power would be 7x to the 3rd. My highest power in my denominator would be 14x squared. If I evaluate my limit as x approaches infinity, I would have 7x to the 3rd divided by 14x squared. If I reduce it, my x's would cancel out, all but one in my numerator. And I can reduce 7 and 14 if I wanted to, which would become 1/2. So I'd get the limit as x approaches infinity of x divided by 2, or 1x divided by 2, however you wanted to write it. If I plug infinity in, I'd get infinity divided by 2, which still gives me infinity. And the last one, when the limit equals the coefficients of the highest powered term. Sorry, I had a typo there too. The coefficients of the highest power terms is when the numerator and denominators are the same power. Should have that. So here I would have 12x to the 4th divided by 16x to the 4th. So if I evaluate that as x approaches infinity, 12x to the 4th divided by 16x to the 4th. Guess what? The x to the 4th cancel out. So I'd get 12 over 16, because I have no x's to plug infinity into, which reduces to 3/4. So you end up with those three cases. If the limit equals 0, if the limit equals positive or negative infinity, and if the limit equals the coefficients reduce. So number 1, if I look at my highest powers, I would have 5x to the fourth divided by negative x to the fourth. Well, my x to the fourth cancel out, but that negative's still there. So I end up with 5 divided by negative 1, which gives me negative 5. Number 2, if I'm looking at my highest powers, I have 6x to the third divided by 3x squared. So that would be the limit as x approaches infinity of 6x to the third divided by 3x squared. Well, I cancel out my x's. I still have 1 in the numerator, so I would have 6 times infinity divided by 3, which ends up being infinity. Number 3, 10x to the 6th divided by negative 11x to the 7th. Rewrite it. So the limit as x approaches negative infinity of 10x to the 6th divided by negative 11x to the 7th. Reduce that by crossing out my x's. I'm plugging in my negative infinity, so I'd have 10 divided by negative 11 times negative infinity. Be careful about your negatives. So I'd end up with 10 divided by infinity, which gives me 0. Whenever you have infinity or positive infinity, negative infinity, doesn't matter which one, in your denominator you're going to end up with 0 for your limit value. Number 4, looking at my highest powers, I got negative 2x and 6x squared. So the limit as x approaches infinity of negative 2x divided by 6x squared. Cross all my x's. And why don't you try to finish these next 3 on your own, and I'll pop back in a little bit to give you the answers. So, number 4, you should have got 0, because your denominator has a larger exponent. And honestly, if you start remembering these rules, you can just skip right to that answer. Number 5, I ended up with the same exponent power, so I get negative 4 over 3. And that doesn't reduce at all. And then number 6, I end up with x squared is larger in the numerator, so I end up with negative infinity if I plug it in and simplify. So L'Hopital's rule will work for indeterminate trig functions as well. Those do not have to approach negative infinity or infinity. You just use the derivative of the numerator and denominator, and then you can plug in. So if I had limit of sine of x divided by x as x approaches 0, I take my derivative, of sine, which is cosine, and the derivative of x is 1. So now I can plug in, because I don't have 0 in my denominator anymore. So cosine of 0 is 1. And when you're typing in pi's, you have to remember you need to type in the pi. And you need to make sure your calculator's in radians. So if I did the next one, the limit as x approaches pi of cosine of x divided by x minus pi. If I typed in pi now, I'd get 0 in my denominator, so that doesn't work. So the limit as x approaches pi of derivative of cosine is negative sine. Derivative of x is 1. Derivative of pi, remember pi represents a number, so that would be 0, so I would get, well, 1 minus 0 is still 1 in my denominator, so I have negative sine of pi divided by 1. If I type in negative sine of pi in my calculator, you get 0 divided by 1, which gives me 0. This next one, if I plug in 1 into my denominator, I'm going to get 0, so again, I have to take my derivative. So derivative of cosine is negative sine, divided by derivative of 1 is 0, derivative of x is 1, so I've got the limit as x approaches negative 1 of negative sine x. 0 plus 1 is just 1, so I don't need to put that in the denominator. If you wanted to, you can, but it doesn't really matter. It's not going to make a difference. So if I plug in negative 1 into sine of x, I get sine of negative 1, which again, you have to make sure you're typing it in radians, because negative 1 would be a radian measure, not a degree measure. There's not a degree symbol there. So that would give me an ugly decimal of negative 0.84147, etc. If I were to type in pi over 2 and a cosine, that gives me 0 in my denominator. So again, you have to take the derivative. So derivative of x would be 1. Derivative of cosine x is negative sine x. So now if I type that in with a pi, 1 divided by negative sine of pi over 2. Remember, it has to be in radians. You get negative 1. This last one's a little bit more tricky because it's a lot more complex function that you're taking the limit of. So if I took my derivative, limit as x approaches 0, the 2 is a coefficient, remember, so that's staying out there. Derivative of cosine is negative sine, minus 2 again is a coefficient, but cosine 2x, you have to use the chain rule. So 2 times derivative of cosine is negative sine of 2x. And then remember, chain rule, you take the derivative of the outside, which would be cosine, times the derivative of the inside, which would be 2x, is becoming 2, divided by derivative of 1 is 0, derivative of cosine is negative sine. So you want to make sure you simplify that first, because it looks pretty ugly right now, before you see if it's indeterminate still. But remember, indeterminate is 0 in the denominator. So 2 times negative sine would be negative 2 sine x. Negative 2 times negative sine times this 2 would become negative 4, positive 4, because the negative times the negative change to positive, sine of 2x, divided by minus a negative sign would become a positive sign in my denominator. So now I have to use my derivative again, because sine of 0 gives me 0, so that doesn't help. Then you do the derivative again and get negative 2 cosine of x plus 4 times cosine of 2x times 2, which you can multiply 4 and 2. But if I plug in 0 into my denominator, I'm not going to get 0. So now when I plug in 0, I would have negative 2 times the cosine of 0 plus 8 times the cosine of 2 times 0, which is still 0, divided by the cosine of 0, and cosine of 0 is 1. So cosine of 0 is 1, so if I plug in 1, I have negative 2 times 1 plus 8 times 1 divided by 1, which gives me negative 2 plus 8, which gives me 6. So copy the notes, do as much as you can of the homework for extra credit, and this is assignment 22 on page 245. If you want to do it, you don't have to do it. I highly suggest you do it because it's helpful. And remember to keep on working on your review for the final.